Given the integral from 1 to 4, the square root of x dx, we will use the Simpson rule to estimate the integral using n equal 12 intervals. We then calculate the error bounds and the exact integral to verify the theorem. We then find an n such that S sub n has an error of at most 0.000001 or 10 to the negative 6 power. S sub 12 is delta x over 3, where delta x is b minus a over n, or 1/4, times the quantity f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 plus and so on, all the way to the next to last term is 4 f of x sub n minus 1 plus the last term f of x sub n. This is approximately 4.666659. Noted that in the separate video, we found that the midpoint rule is 4.669245 and the trapezoid rule using 6 interval is 4.661488. If we were to take the weighted average using 2 midpoint sum and 1 trapezoid sum using 6 sub-interval, we would obtain the same answer, 4.666659, but instead of using 6 interval only for the midpoint and the trapezoid, we would need to double the number of intervals for the Simpson rule, which is 12. B. To find the error bound for the Simpson rule, we need to find k, but k is the upper bound of the absolute value of the fourth derivative. Starting with f of x equal to the square root of x, we find the fourth derivative, negative 15 over 16 x to the negative 7 over 2. We need to find the maximum value of this absolute value function from the interval 1 to 4. Taking the next derivative, which is the fifth derivative, but of the absolute value, we see that it is negative. So the absolute value of the fourth derivative is decreasing. Its highest value must be at x equals 1, the leftmost endpoint. Plugging 1 into the absolute value of the fourth derivative, we have 15 over 16. This upper bound, or the maximum value, is the value k in the error bound for the Simpson rule. The error bound for the Simpson rule guarantees that the error E sub s is less than or equal to k, which is 15 over 16, times b minus a, but b is 4 and a is 1, raised to the fifth power over 180 times n, but n is 12 to the fourth. This is approximately 0.000061, or 6.1 times 10 to the negative fifth power. Since the integral from 1 to 4 square root of x dx can be evaluated exactly at 14 over 3, the actual error is 14 over 3 minus s sub 12, which is the estimate using the Simpson rule, which is 4.666659. This is approximately 0.0000076666, or 7.67 times 10 to the negative 6 power. This is much smaller than the error bound guarantees, so the theorem is verified. Part D. To find the number of n such that S sub n has an error of at most 10 to the negative 6, we use a formula in the error bound for the Simpson rule, where k is still the upper bound of the absolute value of the fourth derivative, which is 15 over 16, b is 4, a is 1, n is unknown, and we set it less than 10 to the negative 6, or 0.000001. Solving for n, we obtain 33.54, but n is a whole number and even, so we round it up to 34. Regardless whether this n or even or odd, we always round up to the next even whole number. Using the Simpson rule with 34 intervals, we will obtain a result whose error which is the difference between the actual integral 14 over 3 and our estimate, that error will guarantee to be less than 10 to the negative 6.